GPT-4 can pass the bar exam. It can write poetry, debug complex code, and explain quantum mechanics. But ask it a simple question: how many R's are in the word strawberry? And it often says 2. The right answer is 3. And this isn't a bug. The model isn't stupid. The answer lives in a hidden pre-processing step that almost nobody talks about. It's called tokenization. And once you understand it, you'll see LLMs completely differently. Here's the fundamental truth about large language models. They don't understand letters. They don't understand words. They only understand numbers, sequences of integers called token IDs. So how do you get from raw human text to something a neural network can process? That's the tokenizer's job. It's a translation layer. It takes your sentence, shreds it into pieces, and assigns each piece a number. The model never sees the original text, it only sees those numbers. And here's the kicker: the tokenizer is lossy. Information gets discarded before the model even gets a chance to look at it. As Andrei Karpathy put it, tokenization is the only part of the stack where a single byte can break your entire prompt. The algorithm that powers most of today's tokenizers is called Byte Pair Encoding. BPE. It was originally a data compression algorithm from the 1990s. Back then, it was used to shrink file sizes. But in 2016, a team of researchers realized it could solve a different problem. Word-level tokenization gives you too many rare words. Character-level gives you sequences that are way too long. BPE finds the middle ground. It learns the most common subword units from your training data. Common words like that and hello become single tokens. Rare words get split into smaller pieces. It's a sweet spot that balances efficiency and coverage, and it made modern LLMs possible. So how is a tokenizer actually trained? It starts with every single byte in your corpus as an individual token. Then it counts every adjacent pair of tokens across all your text. It finds the most frequent pair, say, S followed by T, and merges them into a new token, say. Then it repeats thousands of times. Each merge adds one token to the vocabulary until you hit your target size, typically 32,000 to 100,000 tokens. The result is a hierarchy. For example, Hello World tokenizes to just 2 tokens in GPT-2's tokenizer, Hello and World. That's 2 tokens instead of 11 characters. 5.5 times more efficient. And once training is done, the merge rules are frozen. Your tokenizer never changes, even if the model is fine-tuned later. Now we come back to strawberry. Let me show you exactly what happens. When GPT-4's tokenizer processes the word strawberry, it doesn't see 10 individual letters. It sees 2 tokens, straw and berry. The model literally never sees the 3 R's. It sees a token that represents the concept of straw and a token that represents the concept of berry. Counting letters is impossible when you can't see letters. This isn't a bug in the model. It's a direct consequence of how BPE works. BPE optimizes for compression, not for character-level reasoning. And the same problem extends everywhere. Write hello backwards, the model sees 1 token for hello, not 5 letters. Arithmetic like 24 plus 35, the model sees whole numbers, not digits. Even URLs get swallowed whole. Chain of thought prompting can help a little, but the model is still guessing from its training data. It's not actually reading characters. The strawberry problem is frustrating. But there's a deeper issue that affects millions of people. Tokenization bias. BPE tokenizers learn merge rules based on frequency in their training data. And that training data is overwhelmingly English. So English gets treated like a first-class citizen. Common English words become single tokens. English subwords like ing and tyan get merged aggressively. But what about Thai? Or Arabic? Or Burmese? In English, you average about 1.3 tokens per word. In Thai, it's about 3.7. In Burmese, it's nearly 6. That means a 1,000-word message in Burmese costs almost 5 times more than the same message in English. Same meaning. different price. And since the context window is fixed, say 128,000 tokens, non-English users exhaust it much faster. They get less room to reason and less value for their money. This bias creates a vicious cycle. Non-English tokens appear less during training, so they get weaker embeddings. Weaker embeddings mean worse model performance. Worse performance means less usage. And less usage means even less representation in future training data. The cost impact is real too. Token count directly drives API pricing. A 4 times less efficient tokenizer means 4 times the cost per message. And that 128,000 token context window? For English, that's roughly 100,000 words. For Burmese, it's closer to 20,000. Even named entities suffer. An unusual non-Western name like Srinivasan might get fragmented into 4 or 5 tokens, Sri, Ni, the, San, making the model less likely to recall it accurately. The tokenizer silently shapes who the model serves well and who it serves poorly. So what's the alternative? Researchers have been working on this for years. Unigram LM takes a probabilistic approach, start with every possible subword, then prune the least useful ones. SentencePiece removes space-based pre-tokenization entirely, which makes it much better for languages like Chinese and Japanese that don't use spaces. Then there's byte-level tokenization. Byte 5 uses raw UTF-8 bytes, just 256 possible tokens. No training needed. No language bias. And it completely solves the strawberry problem because the model sees every single byte. The trade-off? Sequences become 2 to 4 times longer, which means more computation. MegaByte tries to close that gap with a clever hierarchical architecture. A global model processes patches of bytes while a local model handles individual ones. It's elegant but still experimental. No clear winner has emerged yet. Tokenization is the silent bottleneck in every LLM pipeline. It shapes cost, reasoning ability, and fairness, and most users never see it. The strawberry problem isn't a bug, it's a design trade-off. Language bias isn't an accident, it's baked into the data. If you're a developer, always check how your inputs tokenize. Tools like TikToken and Hugging Face tokenizers are free and easy to use. Understanding your tokenizer is the first step to understanding your model. If this changed how you see LLMs, hit subscribe. We're doing a deep dive on transformer attention next. And drop a comment with the weirdest tokenization fail you've seen in your own prompts.